In this video, I'm going to discuss something that's called the vector model of angular momentum. Remember that angular momentum is a vector quantity, so which means it has both a magnitude, which is the length of the vector or the magnitude of the angular momentum, and a direction. That is to say, is this angular momentum pointing this way or that way or wherever. Okay, so I'm going to just illustrate this with two different types of angular momentum. So the one you're most familiar with, of course, is the orbital angular momentum from the hydrogen atom quantum numbers N, L, and M sub L. Well, if L equals 1, we know what orbitals those are. Those are the p orbitals, and there's 3 of them. And the reason we know that there's 3 of them is because M sub L can be 1 or 0 or minus 1, or in quantum mechanics, any combination state can have these. But we're going to list more or less just the eigenfunctions and the eigenvalues for the most part. Okay, so this gives the quantity, which is the length of the angular momentum vector. And the magnitude of the angular momentum vector, well, since L squared is L times L plus 1, L plus 1, h bar squared, then the length of the vector is the square root of this. So all right, so the h bar squared, of course, is take the square root of that, we're going to get h bar. Okay, so that's going to be the length of the vector that we're going to draw in space. The other thing we've learned about angular momentum is we can only know one of the 3 components. And the M sub L quantum number tells us the amount of the angular momentum which is along the z-axis. It's in the z direction. So LZ is just M sub L h bar. And of course there's 3 of these. And so what we're going to do is just draw a vertical axis. And we're going to have a 0. All right. And then so the length of this vector is going to be square root L times L plus 1 h bar, or square root 2 h bar. Okay, and the one of the z components is 0, which means angular momentum is pointing this side. So this is one with M sub L equals 0. All right. Now the other component is one that has a plus 1 h bar z component. And so how do you do that? Well, you're going to draw a vector of the same length such that the vertical component has a projection onto the z-axis of plus 1 h bar. All right. And we do exactly the same thing for the minus 1 h bar. So I'll just try to not a perfect artist or anything like that, but those are the 3 possible orientations of an angular momentum where L squared is 2 h bar squared. Okay, so what this means is if you look at a quantum system and you define a z-axis somehow, but maybe looking at the orientation of the angular momentum and measuring the z component, you'll get 3 possible answers. Only one of these answers you will get when you actually make a measurement on an individual system. So some of the times, maybe it depends on what state it's in, you might observe the angular momentum with a particular angle respect to the vertical so that the z component is plus 1 h bar and the length is square root 2. All right. And so that, or you might see the angular momentum exactly perpendicular to the axis that your measurement determines as z, and minus 1. Well, what about the x and the y components? Well, in the spherical polar coordinate system, remember the polar axis is the z-axis, but the great circle that defines the equator is the x and the y, but we don't know what the x and the y components are. All we can tell is that it can be anywhere in the xy plane. We do have some restrictions on the length of this vector. It can't the length of the component in the xy plane can't be longer than the length of the vector. That's impossible. All right, but it's completely undetermined. So that's why you will see figures like showing cone for this guy. Okay, so that this thing precess about the z-axis such that the z component doesn't change, but the x and the y's constantly do. Okay, and that's one of the consequences of Heisenberg uncertainty principle. We actually can't know the y or the x components. If we try to determine those, that actually messes up the eigenfunction as far as what the actual z component is. Those get scrambled. And there's no way to actually fool this. You can't measure the z component, determine what it is, and then measure the x component, determine what it is. What that does is mess up the wave function, and it's no longer an eigenfunction of the z operator. Okay, what about something else? It turns out that angular momentum can also be a half integer type. So one of the examples that you might learn in Gen Chem is the spin of the electron, and that is a spin of 1/2. What happens with the half integer spins is there's not an integer spin component, so there is no 0, so there's no pointing out exactly to the side. And the z components are plus 1/2 h bar and minus 1/2 h bar. Okay, this is the m sub s quantum numbers you learn about for the spin of the electron in general chemistry. And of course, the length of the vector is going to be the square root of the spin quantum number times s plus 1 h bar. So s equals 1/2 for the electron. That is one of the properties of the electron. If it spins not a half, then it's not an electron. So when we say spin of the electron being up or down, we're talking about the z components up or down. The spin of the electron is the length of its angular momentum vector, and that's just a constant. Okay, what about j equals 3/2? Well, with j equals 3/2, whoops, the steps are half integers. Sorry, the steps are integers with half integer components. No integers, okay? So the origin, so you have one pointing that way, one pointing that way. Again, none exactly to the side. And then one pointing this way, and one pointing that way. Okay, and trying to get their lengths all more or less the same. The length of this vector is going to be the square root of 3/2 times 3/2 plus 1, which is 5/2 h bar. Okay, so that's going to be the square root of 15 divided by 2. So that's the magnitude of this spin angular momentum, and the spin quantum number is 3/2. And it has 4 possible orientations. So actually the number of orientations is going to be 2 times the quantum number, L or J, plus 1. All right, well that's it for the vector model of angular momentum. I'll see you in class soon.